Hi, I'm Dan Schatzberg, and I'm a research scientist at Meta, and I'm presenting joint work with my colleagues at Meta and Carnegie Mellon University. The work is titled IOCost, Block I/O Control for Containers in Data Centers. The context of this work is that we've entered this new era in data center computing where containers have become ubiquitous. There are many open source container runtimes like Docker or runc or containerd, and the key feature of containers is that they virtualize resources at the OS layer. At Meta, we've adopted containers ubiquitously. They're lightweight, they're fast to bring up, and they offer a lot higher consolidation of our compute resources. You can see some of the papers I reference at the bottom for more details on our container infrastructure. But one of the problems this has led to is that resource isolation has become a lot more important, where resource isolation is just our ability to ensure that each workload gets sufficient resources despite being co-located with many other workloads. It's a fairly well understood problem for compute, memory, and network, but what we found in our work is that there's this missing piece of how do we ensure resource isolation for block I/O, where storage devices like SSDs or hard drives need to be shared across multiple workloads. One might ask, why do we even need block I/O in the data center? Well, for one, we have storage systems like Zookeeper or MySQL that explicitly read and write to the storage device. We also have a category of software that does system updating or package fetching to keep the machine up to date. And while none of this is particularly important to have happen timely, it shouldn't interfere with the work of the primary workload. And finally, we have a category of block I/O we call memory offloading, where storage devices may participate as part of the memory hierarchy, and as memory goes unused, it can get offloaded to the storage device. For more information on this, you should see our paper at ASPLOS called TMO, Transparent Memory Offloading, where we talk about this in more detail. There are a number of challenges with I/O control, and one of them is that we have a lot of hardware, and it's very heterogeneous. We have multiple generations of SSDs, hard drives, they can be local or remote, and even within one of these categories, we have different performance characteristics, where some SSDs are particularly fast, some are slow. You can see our paper for some breakdown of the various devices in the Meta fleet. But even with that, we have idiosyncrasies of each device. So, say SSDs that have a lot of buffering, or some that go into long-term garbage collection cycles, and all of this has an impact on I/O performance, and therefore an impact on I/O control and ensuring isolation. The next challenge is that our workloads are also heterogeneous, where, simply put, I/O control needs to cater to a wide variety of workloads. We may have databases, video and video encoding, we can have our website, and function as a service, all of which have varying characteristics. Some are latency sensitive, while others care more about throughput. Some are read-heavy workloads, while others are write-heavy workloads. And then there's mixtures of sequential and random I/O, which can cause all sorts of different performance behaviors on a device. The final category of challenges is what we call Datacenter Requirements. Simply, at scale, we need to provide a number of different features. One is ease of use, where, say, I want to share an SSD across a low-priority workload and a high-priority workload. But how do I configure this? Is it in terms of time, in terms of bytes, in terms of IOPS? This is difficult for me to configure, let alone one of our service owners. The next category of features we want is work conservation, where in the same scenario, a low priority and a high priority workload sharing an SSD, we wonder what would happen if the high priority workload stops using nearly as much. And if you just naively limit what everyone can do, the low priority workload can't use the otherwise underutilized throughput of the SSD. The final category here is memory awareness, where we have scenarios where a low priority workload through the memory subsystem can actually end up causing quite a lot of I/O. And if we're not careful, there's a big opportunity for priority inversion where they end up dominating the SSD over the high priority workload, simply through their memory access. What we're presenting here is IOCost, and it's an I/O controller implemented in Linux which provides isolation. And the core idea behind IOCost is that we can model device occupancy offline to account for various differences between devices. And then we can share that I/O through proportional I/O control. And we configure this in terms of weights so that one container can get 75% of the occupancy, another can get 25%. This is for ease of use. And then finally, we have a lightweight work-conserving budget donation algorithm where underutilized portions of the budget can be donated to those workloads that want them more. IOCost manages I/O across the entire Meta fleet, and we've open sourced both our device profiling and our benchmarking tools, and the IOCost controller itself is upstreamed in Linux. In the next few slides, I'm going to talk about IOCost Design and get into some more details. To start with, I want to talk about how it's configured. And here we use Linux C groups. Linux C groups are just a group of processes that you can attribute resources to and do various controls on. And IOCost, the way we control it is through weights. So each C group is given a weight that determines how much I/O it should be assigned. So in this case, I have two C groups, A and B. Each have equal weight, therefore they should each get half of the I/O. And this is hierarchical, so I can have C groups C and D that are children of B that share that half that B is assigned proportionally. And the key thing is that weights really only compare from across siblings, not across parent and siblings. So I can say C group D should get 4 times the I/O of C group C just based on their weights. Internally, what we do is we multiply all of this to calculate what we call the H weight, and this is the overall proportion of the I/O that each C group should get. So A should get half of the I/O, B should get half, C and D in the 4-to-1 ratio that we talked about, but sharing only B's half of the I/O, C gets 1/10, D gets 4/10. And we track this throughout the system so that whenever process issues I/O, we figure out what C group it belongs to and we know what H weight it should be assigned. Next, I want to talk about the IOCost issue path, and ultimately this is the hot path where an I/O comes into the system and we need to make a determination. Do we issue it to the device right away or do we block, and if so, for how long? And an I/O in Linux is represented by a bio, which tells us how many sectors are being read or written. We can determine based on previous bios if this is sequential or if it's random. It has a lot of properties to it. And we feed this into something called the Occupancy Modeling component. I'm going to get into some more details in a little bit, but the important thing is that for now, it just outputs an absolute cost. And this tells us how much of the device is being consumed by us issuing this. I'll get into some more details on that in a little bit, but it allows us to make this block or don't block decision very easily. We take into account the C group configuration to scale that absolute cost. So divide it by the H weight and we get the relative cost. A C group with very low H weight has a very high relative cost, and a C group with very high H weight has a very low relative cost. And this we compare with what we call the V-time budget that is also tracked per C group. It roughly follows wall clock time, but we boost it in certain occasions when a C group hasn't been issuing I/O for a long time. And this tells us how much of the budget has a C group already consumed. We compare the relative cost to the remaining budget. If it's over budget, then we don't issue. We block until the budget has been replenished. If the budget is sufficient, we issue right away. And with occupancy modeling and cost scaling being fairly low overhead operations, this happens very quickly on the issue path. I want to get into some more details on the occupancy modeling because it's really core to how this all works. And what occupancy modeling really does for us is it captures all these device differences, how well it handles random I/O versus sequential I/O or reads versus writes. And the way to think about it is that the cost of an I/O, what we get out of this occupancy modeling is it's in units of time, but it's not a measure of latency. So if the output says this bio takes 10 milliseconds, that doesn't mean that the bio is going to take 10 milliseconds to complete. It means we can issue precisely 100 of these per second. Right? There may be multiple in flight at a time, but 100 of them per second, the device, if we were to send more of that, we would overload it. And in our work, what we've done is we've used a linear model, which we estimated offline. So for each device in our fleet, we use synthetic saturating workloads that say just issue as many reads as we can of 4 kilobytes, or as many large sequential writes as we can. And we see how many can the device take, and this gives us 2 parameters, this base cost for each I/O and the size cost rate, how much that the cost scales with the size of the I/O. And both of these parameters depend on whether it's a read or a write, or it's sequential or random. You might ask yourself, well, how can this work, right? And the mixtures of reads and writes might not just linearly stack together like this. And indeed, we might just have inaccurate models where our synthetic offline analysis doesn't come up with something that easily works for the devices in production. I'm going to leave that detail for the paper, but very briefly, the important thing is that we can adjust the overall issue rate of the device, what we call the V rate. And this allows us to slightly underutilize the device according to our model and still maintain good control. The next thing I want to talk about is budget donation, and this is the key component that ensures work conservation. So consider the following scenario where I have 2 containers A and B. A has an H weight of 1/3, B has an H weight of 2/3, and they're each issuing I/O. As we can see here, we periodically do this planning phase. So in this first period, both of these containers have issued I/O and independently go through this issue path. And we recognize that actually container A has issued more I/Os than it can. They've queued up and blocked. But container B has underutilized its budget. So what we do is that the next planning phase, which happens every 100 milliseconds or so, we determine, okay, container B is underutilizing its budget. We're going to donate it to container A. And then on the next period, container A will have this 2/3 H weight, and container B only has this 1/3 H weight, which is sufficient for the rate that it's issuing. And therefore, all these other I/Os can go through for A. On the next planning phase, if everyone's using their budget appropriately, there's no donation changes. But what can happen is in the next phase, B may issue more I/Os and actually want to demand more of its budget back. And we do allow for a donation to be rescinded in the issue path completely. So that would block A's future I/O submissions and not overly penalize B for donating. In the next slides, I'm going to cover some evaluation of IOCost itself. To start with, I want to evaluate proportional control. How well can we share I/O across 2 containers? So in our setup, we use 2 containers running FIO, which is a standard benchmark, and we configure it to just send as many 4K reads as it can, so long as its measured latency is under 200 microseconds. This sort of replicates, say, an online service that does a little bit of I/O, but would have to load shed as soon as it starts seeing too much latency. And for our purposes, what we're interested in is a target ratio of 2:1, where the high priority workload gets twice the amount of I/O as the low priority workload. And we ran this for a few different existing I/O controllers. First, we used BFQ, which does allow for configuration in terms of weights, just as IOCost does. But its ability to control latency doesn't work too well. In our findings, we saw it way over prioritized the high priority workload, and the low priority workload suffered way more than it should. We also compared with an I/O controller called IO latency. This is one that we developed ourselves when we initially started tackling this problem. IO latency allows you to configure not in terms of weights, but in terms of latency targets. And while this can be good for having strict priority ordering, it's not great for proportional control, where you want 2/3 of the I/O to go to the high priority and 1/3 to go to the low priority. There's no great way to configure it, and the best we could do is shown here, where still the high priority way over dominates the low priority. Finally, we ran IOCost, and we got our perfect 2:1 ratio, where the low priority gets exactly half of the I/O of the second. We also actually compared with block throttle, which is an I/O controller that sets limits. And here you can see the power of setting limits. Based on the measured IOPS we got out of IOCost, we were able to limit the low priority and the high priority accordingly, and they each get exactly 2-to-1. But we wanted to get into the other component here, which is work conservation, where we replaced this high priority workload, sending 4K random reads as long as latency is less than 200 microseconds, with one that just sends a 4K random read and then waits for 100 microseconds and then issues again. This is much lower I/O throughput, and we expect correspondingly the low priority workload should be able to consume a lot more of the I/O. And what we see when compared to block throttle is that, well, this is the cost of limits. The high priority workload still consumes as much as it consumes, but the low priority workload way underutilizes the device. Compared with IOCost, we have this big difference, where IOCost allows much more aggregate I/O and shows the value of our work conservation. I'm going to talk about one more production workload, and this is our Zookeeper workload, which the Zookeeper, for those who don't know, it's oftentimes considered a configuration storage system or synchronization storage system where metadata or locking information can be used, and it's strongly consistent. So there are multiple replicas. They all kind of broadcast their next commit, all agree to the commit, and then write to disk. So very write-heavy workload, and one where latency is quite critical, particularly because there's an ensemble of replicas that all need to make progress at the same time. And in our production use case, Zookeeper has about a 1-second commit SLO. And we ran with various different controllers with BFQ, block throttle, I/O latency. We found the latency was terrible. And over a 6-hour run, many SLO violations across all of the different controllers. We enabled IOCost and we saw instantly much better latency. Only a couple violations here and there, oftentimes due to large commits. I'm going to sort of close out here by talking about a little more of what's in the paper that I can't cover here in this talk. First, memory awareness, not something I got to here, but how we avoid this priority inversion is something you can look for in the paper. The exact details of our budget donation algorithm, which is quite novel, also in the paper. And there's a lot of categorization of both our hardware and workload heterogeneity across the fleet. Our evaluation itself is pretty comprehensive. We talk about overhead, some of the disk modeling and how the V-rate adjustment works. We talk about various overcommitted environments where memory ends up swamping the disk. And we do comparisons with remote storage and VMs. We also provide some fleet information on how well IOCost has solved some of our package fetching or container cleanup operations. I'm going to summarize here some of the takeaways of this work. One is that our use of device occupancy with both offline cost and quality of service modeling allows us to take into account various device differences across the fleet. And this allows us to do proportional I/O control through weights, which contributes to the ease of use of I/O control. Finally, we have a lightweight work-conserving budget donation algorithm that allows us to preserve good utilization of our device. IOCost manages I/O across the entire Meta fleet, and we've open sourced both our device profiling and benchmarking tools, and it's all upstreamed in Linux. Thanks, that's all I have, and appreciate your time.